The second experiment. In this experiment, linked again with the name ORI, we have checked the ECG spectrum near the VLF region, as the VLF was absent in the ECG spectrum for the resting state in the first experiment. The question was whether such a result persists in all ECG spectra. Therefore we have probed the VLF region by monitoring very prolonged breathing with a rate of 0.04 Hz. For the spectrum of RR intervals, we found that the DFT, spline interpolation, and NUT give similar results, and again NUT was practically identical to the spline interpolation. Therefore we present only the results of NUT, which are presented in A. For comparison, the spectrum of the ECG signal is given in B. In A, one can see a very clean pattern of a peak at 0.04 Hz and its higher harmonics. In B, one can see a similar but somewhat diffused pattern. Thus this experiment indicates that similar respiratory patterns exist in both the RR and in the ECG signals. The relative power computed, from the ECG signal of ORI with breathing rate of 0.04 Hz, by two different methods, in the spectral range of 0 to 0.62 Hz, A, by NUT, B, from the ECG signal. The third experiment. In this experiment, linked to the name Alex, who is one of the authors, AG, very fast breathing was accurately monitored at the rate of 74 per minute and 84 per minute, respectively. These rates were well above half of the average heart rate, thus allowing to observe in detail the development of aliasing. In the ECG spectrum is dominated by the very high and narrow peak at the frequency f1 equals 1.234 Hz, also its higher harmonics can be distinctively seen. The frequency f1 is just the breathing frequency 74 per minute in the same figure. One can also see the diffuse peaks near the average heart rate frequency of 1.636 Hz and its higher harmonics. One should observe aliasing at about 1.636 Hz minus f1 equals 0.402 Hz. Indeed, one can see diffuse peaks around that frequency in A, which displays the power estimation of the RR intervals using the NUT, which the Nyquist rate below is similar to the spline interpolation. The width of this region can be estimated by noting that the RR intervals have different instantaneous sampling rates which are equal to the inverse of the RR interval time. And we have calculated the distribution of the sampling rates by dividing the frequency region into 100 beans. We have shifted that distribution by subtracting f1. As one can see, the results are confined approximately to the region 0.32 to 0.47 Hz. Indeed, the aliasing peaks appear in this region. The pictures below the Nyquist frequency are very similar for the DFT, NUT, the spline interpolation, and the LAM method, B, with a similar aliasing behavior. The relative power of the ECG signal of Alex with a breathing rate of 1.234 Hz. The relative power computed, from the ECG signal of Alex with a breathing rate of 1.234 Hz, by two different methods, in the spectral range of 0 to 1.5 Hz, A, by NUT, B, from the ECG signal. A 100 bin histogram of the heart rates of Alex which are subtracted by the breathing rate of 1.234 Hz. In principle, the NUT and the LAM methods should not be used above the Nyquist frequency. Surprisingly enough, we have found that both methods have a sharp peak at f1, as can be seen in the A and B. Both methods do not have the aliasing symmetry of the DFT as given by 17, therefore the results are not symmetric with respect to the Nyquist frequency, half the sampling rate, as it is satisfied, for example, in the case of the spline interpolation. We have found an exact result at f1 and a diffused aliasing around 0.4 Hz. It is interesting to note that both methods give almost the same result below and above the Nyquist frequency. One can interpret the appearance of the sharp peak at f1 as a result of a partial destruction of aliasing symmetry due to uneven samplings. Similar results for the breathing frequency 84 per minute are presented in figures 11 to 12. The relative power of the ECG signal of Alex with a breathing rate of 1.404 Hz. The relative power computed, from the ECG signal of Alex with a breathing rate of 1.404 Hz, by two different methods, in the spectral range of 0 to 1.6 Hz, upper figure, by NUT, lower figure, from the ECG signal.